Um, let's see. All right, I have audio. Well, welcome everybody. I'm very pleased to introduce Jamie Gabbay. He's going to be presenting today about what is an EUTxO blockchain, and I'm really excited to find out the answer to that question. His background is as an academic researcher at Heriot-Watt University, studying the logical foundations of mathematics and programming, and in particular, studying nominal techniques in nominal sets, which is a really interesting subfield to me, at least. Yeah, I'm super psyched to have him here at Galois, and I'm very excited to see the talk. Take it away.
Kenny, thank you very much. Hello, everybody. Hello. Can I please ask everyone to mute your microphones, please? Yeah, good, thank you. That applies to you too, Richard, thank you. And I'd just like to practice a little bit of feedback here. If you have skin, could you please raise your hand in the Zoom meeting? Mike Dodds has skin. Excellent. Okay. So you might need to fiddle a bit to find the raise hand thing. With me, I have to tap the screen, click on more. It's a bit awkward. But please find that raise hand button. Thank you. You can put your hands down now, please. So I can see this. And I'm going to use this in the talk to check feedback. This is, bear in mind, the only feedback I have. As far as I'm concerned, I'm sitting in a room in Glasgow speaking to myself. So if there's something troubling you or slowing you down or confusing you, please do not hesitate to put up your hand or send a chat message or just unmute your microphone and interrupt. That's fine, I'm here for you. Is that clear? Please raise your hand if it is. Looking good, thank you. I've got about half, yeah, this is more like it, okay. There's still 20 of you need to find out how to raise your hand. I'll leave you to work on that as homework. Okay, so good. Thank you very much for coming. It's a pleasure to be here, it really is. This is what research is all about, isn't it? Sharing your ideas. Thank you very much to the team at Galois for giving me the opportunity to tell you about this material. And this talk is based on joint work with Lars Brunius, who is a very nice man. And I'm just going to say this now before I forget, which is that everything I'm going to say applies to the EUTxO model, which I'll explain in a moment. In future work, I would like to do something similar with Ethereum. So if there are any Ethereum wizards out there with whom I could talk and we could have some kind of conversation about how this kind of maths could be done, please get in touch. I really want to hear from you. What follows has been implemented in Haskell. So let's see, do I have a hand? No, not. I won't, there's no pointing device on my tablet, oh well. So the code is there, the package is there, you can fetch the source there, and there's also a journal paper which has very recently been submitted. If you like the maths in here and you want to know more, that journal paper is your first port of call. Please, hands up if all of this is clear. Martha, thank you very much. Hands down, please. Does anyone have any questions so far, by the way? Okay, so I will carry on. By the way, the journal paper, I should have put the title. No prizes for guessing this. The title of the journal paper is What is an EUTxO blockchain? Okay, so let's start with this. Let's look at these equations here. Perhaps I should tell you a little bit about the history of EUTxO. So Bitcoin is based on the idea of a UTxO, which stands for unspent transaction output. And I'll show you a diagram of that shortly. This was extended to extended UTxO. extended UTxO exists in the literature as an inductive definition which takes up a full page in a technical report. And I started thinking about this because it was just too complicated for me. I couldn't understand the mathematical intention behind this complicated definition. And to be clear, I'm not knocking the authors who are super smart. They know exactly what they're doing. But I didn't know what they're doing, and I needed something more compact. So I put on my mathematician's hat and I condensed down this definition to these 4 equations. Now I really do, Richard, I thought of a lot of stuff, but I didn't think of, aha, hang on a second. Now, spotlight perhaps? Oh, good. Can you, hands up if you can see me pointing. Oh, phew, good. Thank you very much. Okay, so this is why I called it idealized EUTxO. It's an idealization of one of them. So here we have simple type equations, and I will just run through how to read this. So yes, so you might be tempted to stare at the blockchain type here, but actually it's the chunk type which will be the real hero of this talk. So this thing here, lurking behind blockchain, this is, in my opinion, the mathematical structure that we should really be looking at. So now, of course, to go to the next slide, I need to exit. Right, sorry, just a bit of a usability problem here. I'm going to press back. And of course, that exits me from Zoom. Interesting. Okay. Now I go back. I see. Okay, that makes sense. I now understand how this works. Okay, so let's look at the inputs first. So let's look at alpha, sorry. Alpha is a base data type for a blockchain. So the idea of a blockchain is that it's some kind of distributed ledger. That's a canonical intuition. So we need some way of storing data on the blockchain. We put it into alpha. I'm just going to take, it's fine if you take alpha to be the natural numbers, if you believe in Gödel encodings. Just a basic question. Hands up if you don't know what a Gödel encoding is, please. Hands up if you do know what a Gödel encoding is. Oh, did I speak too soon? Okay, hands down again. I'll try this again. Hands up if you don't know what a Gödel encoding is, please. Cool, no problem at all. So a Gödel encoding is a fancy way of saying that you can encode any data as a number. For example, I have, I don't know what, a few terabytes of storage in my hard drive, and in principle, that could all be encoded in a huge number. It's not even hard, right? You just print out the contents of the hard drive as a bunch of numbers, and that is your Gödel encoding of my hard drive state. Hands up if that makes sense, please. Thank you, perfect. So when I say that I don't really care what alpha is, it's because I don't care about efficiency for the purposes of this talk. So we know that any data we have can be squashed down into the natural numbers. It's fine. Okay, atoms is a countably infinite set of location identifiers. Each input will get a unique identifier. So here, you see this thing here? An input is a pair of a location, a place, a pointer if you like, and a bit of data. Perfectly simple. And an output is a validator located at a position. Okay, if you have any problem with that, put your hand up, please. Cool, thank you. Technically, atoms are taken from Zermelo-Fraenkel set theory with atoms, but saying that is a bit of a joke, because all Zermelo-Fraenkel set theory with atoms is set theory with these atomic elements added. So in a sense, this is a rather circular statement, but it doesn't matter if you care about foundations. Is it okay if I move on to the next slide? Hands up, please. Cool, I'll take that as okay. Thank you very much. Now, an input, yeah, I've said this, an input is a datum at a position. An output is a validator at a position, and a validator is a set of transactions. So in the industry, a validator is taken to be a script, and the script is applied to a transaction to decide whether it's a valid transaction, whether it's good or not. So all I've done is a standard mathematician's trick of identifying a program with the graph as its function, which is just, in this case, a set of valid transactions. So that's how this happens. We don't take the full power set, and there's several reasons for this, but one, if you just think about it, is that we expect a validator to be a computable set of transactions because we're interested in implementing these. So that's where this subset is coming from. And a transaction is a list of inputs and a list of outputs, subject to some validity constraints. You can't just chuck in any old list of inputs and outputs, but that's good enough for now. That's where this subset comes in. So a transaction is something that has some inputs pointing left, and they are located at locations with some data, and some outputs pointing right, which are also located at some locations with some validators. And if you think about it, we can see how this system is going to be pluggable, because we're going to plug the transactions together. And obviously, this validator is going to somehow check the transactions that are plugged into it. And only if the output is happy and validates the inputs it's pointed at, will the transactions be allowed to be combined. Can I go on to the next slide, please? Hands up if I can go to the next slide. Okay, hands down, please. Are there any questions so far? Okay, good, good. I will continue. Here's a picture. So here we have a transaction. It has 3 inputs. The inputs are located at A, B, and C, and it has 2 outputs located at D and E, and V1 and V2 are pointing to the future, waiting for further transactions to connect to them on D and E. And A, B, and C are pointing into the past, trying to find outputs located at A, B, and C, to which they can pass the inputs x2, x1, x2, in fact, to which they can pass the entire transaction for validation. I hope that makes sense, but if you have any questions, you have to tell me by asking a question, because I can't read your mind from this distance, okay? Now let's just go back. So there you are. So what I'm saying is that a solution to these type equations, some set of input, validator, output, transaction, and chunk, when taken together, allow us to draw this picture. Okay. And a chunk, oh, what have I done here? I've just inlined some of these definitions. I wanted to get this as compact as possible. So, there's always a bit of a tension between being, there can be a tension between being compact and being readable. So I reckon this version is more readable. And here I'm trying to make a point that it really is very simple. We actually have just 3 equations that sum up the structure of a EUTxO blockchain. So that's a point I'm being made. A chunk is a list of transactions, and recall, a transaction is a pair of a list of inputs and a list of outputs. So a chunk is a list of these things. Perhaps I should have mentioned that square brackets is Haskell notation for list of. Subject to some validity constraints, and here they are. So each input in a chunk, so each one of these things here, must have a unique position amongst inputs. So for example, if this input here had been called A, and this input had also been called A, then this would have been an invalid transaction, and it would have made for invalid chunks. You can't have 2 inputs with the same name. Likewise for outputs, you can't have 2 outputs with the same name. In other words, everything has to be at a unique location. However, an input can share a name, a position with an output, in which case the input points to that earlier output. And yes, I should have said outputs come first. So you have an output at a position and then an input that points to that position. And if an input points to an earlier output by citing its position, its location in the chunk, then the output must validate the transaction that the input points from. So here, this output here, it's at a location and it's waiting for a transaction to point, an input to point to it from a particular transaction, at which point this output will decide, using the power set, using its validator, whether it likes that input or not. Let's take a simple example. If you go to a hotel, they'll give you a key card, and when you wave that key card, when you point it at the scanner in the hotel, it'll either let you in or not. So there's a little validator in there that when you put your key card literally in the same position as the scanner, will apply a validation and either reject or accept your input connection. And of course, then you go up to your room and you scan again, and there we jolly well hope that the validator is more stringent about what it will validate. Hands up if that's okay, and I can carry on to the next slide, please. That's good, thank you. Hands down, please. Does anyone have any questions? Could somebody make up a question of some kind just to reassure me that you exist? I'm beginning to feel a bit lonely here. I'm sensitive, you know. Nathan, yes, go ahead. What's your question, please? Don't forget to unmute your microphone.
Whoops, yeah, sorry, same double mute problem here. I guess are the validators able to be arbitrary Turing machines?
Now, that's a good question, and I love that question, thank you. On the face of it, your question is a category error because I just put a power set here. So there's no notion of computation. This is an entirely mathematical model. Hang on, I want to point there. This is just validators that live in here are just arbitrary sets of transactions. I have impose no conditions on computability. I haven't said how these sets are computed. In practice, however, you've touched on a debate. Should the language of validators be Turing complete or not? Now, in Bitcoin, the language of validators, correct me if I'm wrong, is not Turing complete. Whereas in Ethereum, the language of validators is Turing complete. When I say language of validators, what I mean is that there's a script language which generates elements of, which generates these sets of transactions. Does that answer your question, Nathan?
Yeah.
Okay, thank you very much. Keep the questions coming. I've just had a question. I'll paraphrase it. How long are you going to keep speaking for? The answer is until 6:30 my time. I started at 5:30. It's a 1-hour lecture. Okay, let me continue. Thank you for the question. So here are some chunks. So I'm telling you now, these are all chunks, okay? So let's look at this. This is a chunk. It consists of 2 transactions. This is a chunk. It consists of 2 transactions. And this is a chunk which I made. This is so exciting. I made it by plugging this chunk into this chunk. And do you see how, just by concatenating these 2 lists of transactions, this output is now deemed to have connected to this input? It's cool, isn't it? And this output here connects to this input. And this connection thing, all I've done here is I've taken 2 lists of transactions. Remember, a chunk is a list of transactions. So this is list concatenation. I've taken this list and put this list after it. And by definition, the output, the E output of TX2 is deemed to be pointed to by the E input of TX4. And I've written a blue here because fortunately for us, the validator on this output likes this transaction TX4. TX4 is inside the validator in position E of TX2. Okay, I will move on, but do not hesitate to interrupt if you need to. Okay, I like the questions. Can a single transaction give the same name for one of its inputs and one of its outputs? No. So the question, as I understand it, is can you have a transaction with an input located at A and an output also located at A? No. However, that is completely reasonable future work which is actually discussed in the journal paper. So that would give you a loop. It would give you a transaction with a feedback loop. There's an output that's pointed to by an input on the same transaction. Nothing wrong with that. It's excluded in the EUTxO model as presented in the literature, but this is a natural generalization. Thank you for the question. Did that answer your question? Perfect, thank you. Okay, so let's just reflect a little bit on what chunks look like. They look like a data type of abstract syntax with binding. Abstract syntax is just, how could you describe it? It's just, you know, like text and keywords and stuff. So chunks are literally just lists. And the role of positions is reminiscent of process calculi, pi calculus channels. Chunks have dangling inputs. I call them unspent transaction inputs. They have dangling or free outputs. This is the UTxOs. That's these things here. There's also an obvious, a natural notion of alpha equivalence of positions. I will just go back for a second. We see here that we have a position E, and clearly the essential nature of the chunk would not change if we change that position name to E primed. Now, to be clear, I haven't defined alpha renaming on this chunks, but it's clearly there implicitly and could be defined. So there's a notion that when an output connects with an input, then this now becomes a binding of some kind. So this is reminiscent of structures that are seen frequently in computing. And then a blockchain, and that's significant, right? It's good. It's good that these structures look like things we already know, because it means that we know how to deal with them. When we recognize something, it gives us a toolbox to deal with it. And then a blockchain is simply a left closed chunk. A blockchain is a chunk with no dangling inputs. So let's go back again, take a look. Hands up if you think that the top left chunk is a blockchain, please. Hands up if you think it's not a blockchain. Hands up if you don't know. Cool. Thank you very much for your honesty. So let me ask you this. Do we see any dangling inputs? A dangling input looks like this. It's a thing that's pointing left and is red because it hasn't connected to anything. So are there any dangling inputs here? No, they are not. So is the top left chunk also a blockchain, please? Sorry, hands up if you think it is. I agree, perfect. Okay, is this chunk a blockchain? Hands up if you think it is a blockchain. Excellent, okay. Richard, you've got a really great class of attendee at these talks, you know, I appreciate it. So here we see the dangling inputs, which mean it's not a blockchain. Dangling outputs are fine, right? But blockchains like dangling outputs. These are unspent transaction outputs. So a dangling output is like having cash in the bank, right? This is good. A dangling input is bad. It's because you need a resource and you haven't been given it. And then this thing is also a blockchain because, again, there are no dangling inputs. And what's happened here is that this B has connected with this B. Were this B instead a D, then this would not be a blockchain for two reasons. First of all, this B would still be dangling, but also there'd be two outputs called D. So that would in itself be an instant fail, right? So if we just turn this B round, turn it into a D, then this fails to be a chunk. It fails to be a blockchain, but it also fails to be a chunk. That's what I meant to say. Okay. Hands up if I can continue to the next slide, please. Good, thank you. So let's see what's next. Right, now, okay. Chunks form an algebra. This is all completely new. Chunks form, oh, can I explain about the pi? Guillaume, do you know about the pi calculus? Have you seen it before? Okay, so just as a matter of interest, no shame, I'm just asking, hands up if you have seen the pi calculus. Quite a few, but not everybody, that's fine. Okay, so just very briefly, the pi calculus has a notion of an output channel and an input channel. And I'm making an analogy between output channels of the pi calculus and UTxOs, and between inputs of the pi calculus and UTXIs. Outputs and inputs can communicate in the pi calculus very much like outputs and inputs as we see them communicating here. There are clearly differences, and these are described in detail in the journal paper, but one noticeable difference is that here, when we make a connection, the binding intuitively is automatic, whereas in the pi calculus, it's not. And that's simply because the pi calculus is non-deterministic about how outputs and inputs communicate, whereas here, because we insist that there's only ever at most one output and one input with a given position, it feels much more synchronous. It feels much more deterministic, sorry. Guillaume, does that answer your question? Perfect, thank you. Good, great question. So chunks have an algebraic structure. They form a partially ordered partial monoid. If there is a slogan that you take away from this talk, remember this. Chunks are let me try again. Chunks in blockchain form a partially ordered partial monoid with vaguely pi calculus flavored channels. Right? That's the bottom line of the analysis in this talk. The journal paper has much more, but this is a good takeaway message. We've got a partially ordered partial monoid with channels. So a monoid is something with a unit. That's just the empty chunk. And composition is list concatenation. It's partial because of the validity conditions. You can't just throw some transactions together and expect that to make a valid chunk or blockchain. No, you need to validate. This is inherent to the blockchain. This is kind of where the crypto in cryptocurrency lives, right? You're not supposed to be able to just rock up to a blockchain and attach yourself to it. You have to jump through all kinds of hoops to validate yourself that you have the right to participate in this blockchain. So that's where this partiality comes from. And it's partially ordered just by sublist inclusion. And this relies on a theorem which is quite trivial when you notice it, that all of the validity constraints in the system are preserved by taking sublists. Or to put it another way, if you have a chunk and you delete some transactions from it, then you just get another valid chunk. It's just a fact. And it's not true of blockchains. If you have a blockchain and you delete its first transaction, for example, you won't get a blockchain, you'll get a chunk. Interestingly, empirically, I find that chunks are not only mathematically better behaved than blockchains, they're also operationally better to work with than blockchains. And I discovered this from Haskell. I don't know how I'm coming across to you, but you might be thinking, oh yeah, this guy's a mathematician, of course. Hold that thought, please, Hussein. Of course, he's going to try finding algebras, and there's some truth to this, but in fact, I came to this idea from the Haskell. I was writing the Haskell code, and as you may know, Haskell really rewards abstraction. So I was trying to make my code elegant, and in doing so, the code told me I want chunks. Basically, the operations that I was interested in writing on the blockchains demanded chunks. It's very simple why. If you take a blockchain and you chop it up, I'll just go back for a second to show you this. It's a very, very simple observation. Look at the blockchain on the bottom. If we cut it in half, we get a blockchain and a chunk. And if we take a really long blockchain and we cut it up into n pieces, in general, we're going to get one blockchain on the far left and n-1 chunks. So I put it to you that chunks, not blockchains, are the fundamental mathematical abstraction here. Okay, I will move on. Right, okay. Just a couple of meta-level comments. How far am I through? Halfway. Okay, not too bad. In these slides, I'm considering the structural aspects of blockchain. Now, to be clear, this is only a partial account of blockchain structure. For a start, I'm not talking about the crypto at all, but that's okay because there's a clean interface. This is an abstraction, and the crypto side can attach to this abstraction essentially via the validators. So the validators could demand that in order for an input to validate, it has to provide data that solves a cryptographic puzzle, for example. That's how Bitcoin works, for example. Also, this talk is a mathematical abstraction. So it's about a thing called idealized EUTxO, which turns out to be a partially ordered partial monoid. Of course, it's a mathematical abstraction. Practical implementation is more complex, of course. However, these type equations and their algebraic structure bring clarity, which at least I have found very helpful in understanding the Haskell implementation. And also something I forgot to put in these slides is that any algebraic property is also a testable property. So even if you only care about implementing a particular blockchain program, you can still care about algebraic structure because that means testable properties. And if your program fails one of these tests, it's probably a buggy program, right? So even though this maths is abstract, it does serve a purpose, even if you are a hardcore implementer, I would argue. And I'd also add that the Haskell implementation referenced at the start demonstrates idealization as it is, it does have operational content and it does yield executable code. So just to spell this out even further, if you get onto GitHub and look up the file idealized EUTxO .hs, you will find this talk implemented in Haskell and it runs. Okay, hands up if I can carry on, please. Cool, thank you. Are there any questions before I continue? Perfect, thank you very much. Whoops. Sorry, usability issue. Right. So what's original in this talk? Well, not the idea of EUTxO, that is established machinery, and the paper is, well, Bitcoin itself is a UTxO, and it's been extended in the extended UTxO. What is new is the mathematical idealization, idealized EUTxO, which I showed you on slide 4, those type equations. There's also the focus on chunks. The idea that chunks, not blockchains, are the fundamental thing that's being manipulated, that is new. The observation that they have a partially ordered partial monoid is new. And as a matter of fact, this very minor idea of being explicit about UTXIs, which is very natural if you have chunks, is new so far as I'm aware. The idea of equating names of output-input pairs explicitly with alpha equivalents, making it look like syntax, and being reminiscent of the pi calculus is, again, so far as I know, original. See the papers for more. Whoops. Okay, right, let's see what kind of maths we can get out of this. Don't worry if your eyes glaze over over this. I've tried to make it digestible, but you know, it's the first time you've seen this. So I'm going to let variables named ch range over chunks. I'll write pos ch for the positions in a chunk. So you just go down into the chunk and pull all of the positions that are labeling the inputs and the outputs. So there you have it there. The positions of a chunk are its channels. I hope that's clear. And I'll write that ch is fresh for ch primed when they occur on disjoint positions. Let's note that this is a strong orthogonality assertion. It means that the ch and ch primed cannot communicate. Ch has some outputs that are trying to communicate on some channels and some inputs, but they are at different positions from those in ch primed. They can't talk with one another. Hands up if I can carry on, please. Looking good, okay, thank you. Again, I emphasize I can't see your face. Ah, yes, Hussein, please, ask your question. Unmute your microphone, please, and ask the question.
Yeah, I failed to follow remark number 4. Would you mind repeating that, please?
Yeah, sure. So maybe I should just go back to the picture. It's unfortunately a wee while back. So here we have 2 chunks in the top left and the top right. They are not fresh for one another because the chunk on the top left has an E output and the chunk on the top right has an E input. So they share a position E. If I put them together, as I do underneath, they will magnetically lock together and communicate. So that's a case where freshness is not true. And if we take the top right chunk and rename all of its positions to put primes on them, then the top left and the renamed top right chunk are now fresh for one another and they cannot communicate. Does that answer your question? Perfect, thank you very much. We need more questions like that, you know, don't be shy. Okay, and I'll write bullet ch primed when I can concatenate ch and ch primed. So that little dot on the top right, this is just list concatenation. It's literally just writing ch primed after ch as a list. And this is a predicate, a judgment, which asserts that this is a valid thing to do. You know, very simple lemma. If ch and ch primed cannot communicate, then they cannot fail to compose. It's always valid to compose 2 chunks that cannot talk with one another. You can draw whatever parallels you like in real life, right? So it's an orthogonality property. And the proof is just if they don't share positions, they can't interact. If they can't interact, no validators can complain because they never hear from one another. Okay, so it's like they're ghosts to one another. Any questions on that? Okay, this is slightly less obvious. If we can compose these 2 chunks in both orders, then they cannot communicate. They must be fresh for one another. It's kind of obvious when you see it, but it does take a while. The point is, let's suppose this left-hand combination succeeds. And let's suppose that there is some communication, there is a shared position. Then it must be that there's an output in ch that is pointed to by an input in ch primed, because inputs must point to earlier outputs. And therefore, this combination cannot possibly succeed because then the output here that was earlier is now later. Right? So if this succeeds and ch is not fresh for ch primed, yes, Hussein, freshness is commutative because it's a symmetric statement. The positions in the chunk and chunk primed are disjoint. So supposing this is not the case, they share a position, then if ch's output talks to ch prime's input, then here ch's output will be trying to talk to ch prime's earlier input, and that's not allowed. So if this succeeds, then this must fail. So this is actually, I think, really interesting because this is a static property of the chunks, right? This is very easy to verify. It's as simple as going through the syntax and checking for a coincidence of labels. This is an operational property. It talks about whether combinations terminate with success or do not terminate and fail. I don't develop a deep theory of I don't develop observational equivalence in these slides, but if we did, then in fact we'd go further and we'd show this is the start of a theory of observational equivalence which is surprisingly powerful. And I'll try to give you a wee taste. This is the only other bit of serious maths in the talk here. A theorem, it's 3.3.2. I'll run you through it. Forgive me if this doesn't go in the first time. Supposing this thing here is a chunk, so we have ch, and it composes with ch2 and ch1, right? So that's just a list like that. And let's suppose that the dangling inputs of this, so here ch2 has been taken out, are equal to the dangling inputs of this. In this case, ch1 and ch2 must be completely orthogonal and fresh for one another. Why is this interesting? It's an important purity result. Let's consider the case that these are two blockchains. Let's consider a case where ch is the blockchain as it stands, and ch1 is your chunk. This is your contribution that you want to attach to the blockchain. Now, blockchains are distributed systems. It just so happens that one of your competitors may manage to attach their chunk before yours. Now, there's a question. If somebody gets in there first, will it affect the behavior of your chunk? This really matters. This ch1 could be, say, you trying to make a purchase. And this ch2 could be an operation that changes the price of that purchase. So you really care about what effect any competing chunks might have on the state of the blockchain that arrive before your chunk can attach itself. And again, this is a distributed system. So even if you send ch1 off before ch2 is sent off, we don't know which one is going to get attached first. It's impossible to tell. So what this is telling us is that supposing we're at ch, and then we submit our transaction, ch1, to the blockchain, but along the way, and this is what we want to get, right? We want to get one of these, but actually what we get is this, because someone else got in first. If our chunk does manage to attach to the blockchain, then it can't have communicated with the competing chunk, and therefore your transaction is safe. ch2 cannot have changed the price of anything you care about, because if it did, then it would have had to reference one of the positions where the data you're referencing is stored, and then this would have failed. Oi, oi, oi. That was intense. Hands up if you're still feeling okay, guys, please. Not bad, not bad, thank you. Okay, hands down, please. Hands up if you're feeling like your head's about to explode. Oh, that's a bit disappointing. Okay, Richard, I'm not working these guys hard enough. I'll try harder next time. Thank you very much. Okay, so unless anyone interrupts, I'll take it that I may continue. Thank you. So we're going to work through a simple example. I'm going to take alpha to be nat, so my blockchain, my chunks are storing my transactions, my inputs are storing natural numbers. And now we just need to choose these subsets here. Fine, let's do it. Oy vey. So I think what I want you to look at is this I primed here. So this is an input. This is an input, right, sorry, this thing here is a transaction, right? And it's a very simple one with one input and one output. That's all, okay? So the only transactions in this blockchain system are they're kind of unit transactions. They have one input and one output. This input is at a position P and it contains a value I. And then this input is at some other position P primed. If P prime was equal to P, then it wouldn't be a valid transaction. So that can't happen. And what the validator does is it just checks that the input that this output gets connected to is storing I+1. So I put it to you that this is a transaction that is the successor function. It stores I and it tests that the next transaction stores I+1. So if I write this as suc, so this is successor of I at pp primed, and these are my transactions. We admit any chunk provided that positions match up and validators are satisfied. And what that means is, I'm just sort of gesturing in thin air, it means a chunk that, a blockchain that works has to look something like 1, 2, 3, 4, 5, 6, 7, right? So this is a little machine I've built, and validation is just a little counter. That's all it's doing. Any questions before I move to the next slide? Okay. Now, there's a wee proposition here that says that actually there's a homomorphism from these chunks to the natural numbers given by mapping a chunks to its length as a transaction list. So there's a visible sense in which transaction is a successor operation, and we've built a little chunk counting machine. And yes, it is partial, right? Because this system is set up to fail if you try to attach two chunks that aren't counting, but that's to be expected. It's part of the crypto aspect of this model. I'm not going to go into this in detail. I don't have time, and it doesn't really matter, but actually proposition 9 holds of any chunk system. Nevertheless, I think it's illuminating to look at this example and see how we're doing counting. We also note that this previous model doesn't actually have any left closed chunks. It doesn't have any blockchains because every transaction has an input and an output. So any chunk you build will have at least one input and one output, aside from the empty chunk. But that's not a problem for two reasons. First of all, in practice, we don't usually download whole blockchains. They're too big. So actually, even in implementation, we're secretly working with chunks. And also, if we really care about this, we can just add a genesis element, which has no inputs, and a counter starting at 0. So it's not a big deal. Okay, so, ladies and gentlemen, was this a simple example? Yes, it was simple. But I put it to you that more complex examples are mathematically just fancy pants versions of this one. There's no new concepts beyond what I have already shown you, right? What I've shown you is as bad as it gets. Now, this is not to say that blockchains are simple. They are not. And we haven't accounted for complexity and extensions. But don't go away from this saying that, Jamie said that blockchains are easy. They're not at all. But what we have done is provided a new level of abstraction where I feel I like this. I can understand it. I can see what's going on. It's a mathematical structure that abstracts away detail and gives me a clear model, gives us a clear model to guide us. And like I said, this came from the Haskell implementation. I didn't set out to build this maths. The Haskell implementation told me what to do. Could someone please think of a question before I move on? Just to reassure me that you exist. Hello? Yes. Mr. Sorry, who's speaking, please?
Piotr Paradziński. So could you model this thing using Petri nets, maybe?
Sorry, could I model it? Vikram, hold that question and ask me next, please. Could I model it using?
Petri net.
I don't see why not. I'm not an expert in Petri nets, but I know that they are things that join together. That's an interesting thought. Thank you. Can I suggest, if send me an email about this outlining. Thank you, Piotr. Send me an email outlining what you have in mind. Okay, Vikram had a question. Could you unmute your microphone, please, and ask it?
Yeah, hi. Yeah, I was just wondering if there's a categorical model behind this.
A categorical model?
Yeah.
I don't know. Sure, why not?
I just thought you might be interested because I've read your work on nominal sets from a while
Yeah,
ago.
absolutely, absolutely. So actually, it depends what you mean by categorical model. There, actually, in the journal paper, I build a category of EUTxO models and a category of partially ordered partial monoids with channels, and I give representation functors between them that give an equivalence of categories. So one answer is yes, definitely. All of these models organize themselves quite nicely into categories.
Oh, that's very nice. Yeah.
You may have meant categorical model in the sense of giving a any algebra you can also do a categorical analysis of the algebraic structure. That's another notion of categorical model that would be interesting to look at. Yes?
Yes, and yeah, it also ties into the other question because Petri nets are being studied using category theory in the applied category theory community. So that's something.
It would be fantastic, a categorical account of blockchain. I mean, that would be dead sexy. Absolutely.
Right. Thanks. Yeah.
Oh, thank you, Vikram. I also had a question: where is the nominal stuff used? So I had noticed the same. I haven't actually mentioned nominal techniques in this talk. I haven't emphasized that. So secretly, I'm using Zermelo-Fraenkel set theory with atoms to model it. But in fact, and this is discussed in the journal paper, I've had this question before, it's a good one. When you build the most abstract version of this system, which abstracts away, EUTxO, idealized EUTxO, is still relatively concrete in the sense that it is solutions to particular type equations. The partially ordered partial monoid with channels account is properly abstract because you're just assuming an underlying set with operations. There's no internal structure. In order to express the axioms of these algebras, we do need at one particular point to use nominal techniques and freshness. And it's actually latent in this lemma 7. I haven't really brought it out, but the abstract version of lemma 7 does require nominal techniques. But I should emphasize, 3/4 of the journal paper does not, it only uses nominal techniques as a useful language for talking about names. I'm not going to go into that. That's for taking that offline. But thank you for the question. There was a question just before Hussein. Could you unmute your microphone and ask it again? I'm losing the chat messages, so I can't see what you wrote.
So maybe you're asking, yeah. So I felt I was following along at a high level right up until the successor example. And then I felt a bit confused. And so if I'm connecting like locations, so if I wanted to ground this like in how I understand like Bitcoin or something, maybe I could think of positions as like a Bitcoin address plus a transaction ID or something like that. And
yes,
then
that's fine.
Transaction validators are like checking that the sum of the inputs is equal to the sum of the outputs or something like that.
Well, yeah, okay, carry on.
So I guess what confused me about the successor example is if I take that analogy, which maybe that analogy is wrong and that's what you'll tell me, but if I take that analogy, it seems like what we just did was we invented one Bitcoin out of thin air, which seems unfortunate.
Marvelous. Thank you for the question. So the question is essentially, surely we are minting value here, because if this I represents our money, then we have minted a fresh coin here. Now, I hope you will agree that not every blockchain application is necessarily a cryptocurrency. Yes?
Certainly.
Yeah, okay. So there's a cultural thing here which hadn't occurred to me that has led you to interpret this I as an account value, but it's not really. This is just a number, and if you want to think of it like anything, think of it like a clock, right? So the clock validates the next time step when it occurs at the next time step, I+1. Does that make sense?
Okay.
Yeah. So to be clear, this is when I'm not considering cryptocurrencies specifically. I had just built this as the simplest possible example of a non-trivial validator with some mathematical content. And all it does, the only thing this validator does, is literally just check that I primed equals I+1. Now you can drop your own favorite computation into here. Mathematically, I don't care, it doesn't matter. It could be something really complicated. It could be a cryptocurrency. It could be degree results. It doesn't matter. This is a stand-in for put your computation there. Make sense?
I see. So if I want to instantiate this to Bitcoin, then I have to say, what are the collection of valid validators?
Exactly. That's how we control the system. That's precisely right. So the instantiation to particular examples happens in those red subsets there.
Very good. Thank you.
That's a great question. Thank you. Now, there's something else that came up. Yes, so also about Bitcoin. Bitcoin is UTxO. In UTxO, the validator doesn't look at the whole transaction. It only looks at the invoking input. So the difference between UTxO and EUTxO is precisely EUTxO has transaction here. If we want to go to UTxO, then we choose validators that are indifferent to most of the transaction and only look at the first input in the list, in the input list of the transaction. Excellent. Thank you so much for the questions. Are there any more questions before I continue? Okay, cool. So that's great. So this whole discussion has been around my claim that more complex examples are mathematically just fancy pants version of what we've seen. And I hope now you see what I mean when I say that we've simplified complexity and abstracted detail, but it's all in there. It can all, by choosing your right subsets, you can model any arbitrarily complex blockchain. I think I should skip over this slide, but this is basically, I'm making some concession now to practicality. It has to do that in practice, outputs carry state as well. In practice, inputs carry an alpha and outputs carry a little fragment of beta, and the validator, it's just convenient to carry a bit of state, and that's absolutely fine. It's actually what's done in the journal paper. So they are mathematically equivalent, but when you start to write programs, you definitely want a beta there, and that's okay. It's fine. So I must conclude. So in conclusion, thank you very much for listening. What I've shown you is how I've shown you a simple abstract presentation of the EUTxO model, which I've called idealized EUTxO. It's a bunch of type equations. Somebody asked about generalizations, where there are many possible generalizations. And one benefit of the EUTxO model is it invites you to generalize in a way that EUTxO as defined does not. It's not a criticism of the original presentation, but if you go and look up the technical, the original paper on EUTxO, it's an inductive definition. It is what it is, whereas EUTxO clearly invites fiddling and playing. That's what it's for. We've noted that chunks have algebraic properties, and the slogan is a partially ordered partial monoid with channels. That's what these things are. Name binding corresponds to linking outputs with inputs, and this connection is deeper than it might look. There are theorems, non-obvious theorems that can be derived. If you want to, go to the journal paper. It's full of theorems. They come out of this structure. Bottom line is a compact mathematics of blockchains. What I've shown you, I claim, is a mathematics of blockchains. So blockchains as a mathematical structure. And what's in the final slide? Ah, yes, so just summing up, there's a journal paper, there's a Haskell implementation, and yes, so future work, something I'd really like to do, and I don't know enough to do this on my own, is to build a similar idealized Ethereum analysis of Ethereum. Ethereum is not a UTxO system, it's a accounts-based system that has a very different underlying model. It's a completely open question. If we apply a similar line of thinking to Ethereum, I don't know what would come out, and I'd love to figure that out. Thank you all very much for listening. Any final questions before I hand over to Kenny? Okay, Kenny, the floor is yours. Thank you again.
Thank you. That was really fantastic. I'm really excited to dig into the code and the paper. Yeah, thank you so much for presenting. I know it's kind of odd to give a talk over Zoom when you can't have everybody applaud, but I'm applauding from my singular perspective here across the ocean.
Thank you, Kenny. Thank you.
Yeah.
And for everybody, the recording of the entire talk will be on the Galois website. There's a Tech Talks tab, and you'll find Jamie's talk listed there. So that'll be in the next day or two posted. So thanks, everybody.
Thanks, everyone, for attending.
Have a good day. Should I sign off, Kenny, now, or do you want me to stay around?
Richard, what's the next thing for you?
Richard, perhaps you should stop recording.